Okay, so challenge problem number 8. Challenge problem number 8 basically asks us to imagine that there's a disk that is uniformly charged and is spinning around. And it asks us to find an expression that describes the magnetic field strength at the center of that disk. So really you can just imagine actually it says on here, think of the disk as a collection of point charges. So a charged disk is made up of infinitely many little tiny point charges that are connected together, and as it rotates, those point charges will move, and we know that moving charge creates a magnetic field, so the question asks us to find an expression that will give us the magnetic field at the middle of that disk when it's spinning. So with an angular velocity of omega. So I tried to fit all this on one page, so I used less words, but we'll see how this goes. So we know that the expression or the equation that we use to find the magnetic field of a point charge is mu naught over 4 pi times, and I wrote dq instead of q. Normally it's just q, but in this case, if this is our disk with a radius r, capital R, then this little point right here, dA, or change in area, is we can think about this as dq instead of q, which is basically just the change in the charge as opposed to the charge. So in all these steps, when I wrote dq, it's because you can think about this as the change in charge. So times v, and then cross product r hat over r squared. And then also I wrote here you don't really need r hat in this case, because the r hat is in this direction. If you're looking at the disk face on, then the r hat is in the direction that's perfectly perpendicular to the velocity always, because it's a circle, it's always going to be turning, so that velocity is always going to be the tangent to the circle, obviously, and because r is at a 90-degree angle to that velocity, it's always just, as we know, the cross product is just sine theta, and that theta is always going to be 90. So sine of 90 is 1, so it's just times 1. So really, if we wanted to, we could rewrite it in the vector form by multiplying by r on the bottom, but they just cancel. So you get mu naught over 4 pi dq times v, which is a vector, times r vector over r cubed, but then they just cancel. And then you just get mu naught over 4 pi dq equals v over r squared. Okay, so once you have this, then we can put in omega, because we know that as this is turning, we can find we know the angular velocity is equal to v over r, or we can rearrange this to say that this this velocity is equal to omega r, or omega times radius. So, and that's the radius of the disk. So we can put this here. We can substitute for v over r, and because we have v over r squared, we cancel one of the r's on the denominator, so it's mu naught over 4 pi dq times omega, and then that r is canceled, so it'll just be 1 r on the bottom. This should actually just be omega over r, which is, well, I guess that's what I wrote here. Okay, so then mu naught over this is where we start to employ dA, which is the change in, basically the change in the area. We pick an arbitrary point on the disk somewhere, doesn't really matter where. So the area of that point is going to be dA, which is, the area is going to be changing because you pick an arbitrary point, and then, well, I'll get to that later when we integrate. It's basically taking from 0 to r and doing the whole disk. But we know that dq over dA is equal to, basically what this says is dq over dA is the change in the charge over the change in area is equal to the total charge over the total area. So it's kind of like a relative comparison. It's like saying small charge over small area is equal to large charge over large area. And this, you can just state this, and dq is equal to, so if you pull dA, multiply both sides by dA, you know that dq is equal to q divided by a, or charge divided by area, dA. And we know also, because we learned it earlier in the semester, that q over a is equal to eta, which is just charge density. So really, we can just state that dq is equal to eta, which is q over a, dA. Oh, so that's what I wrote here. So dq is equal to eta dA. So then we can just substitute that in right here. So we get mu naught over 4 pi times eta dA omega over r. So we're getting close. What we have to do now is take dA, and we know that that's the area of this small arbitrary point, and so we know that the area of the whole disk, this whole thing, because it's a circle, is pi r squared. So what we can do is take the derivative of pi r squared, and then, it's just how we roll the 2 drops down, and it'll be 2 pi r. So you take the derivative with respect to r. So it's dA over dr, or the derivative of the area with respect to r, is 2 pi r. And then, just like we did up here, we just multiply at the bottom, and then we have dA times 2 pi r dr. And then, again, we can just substitute right into what we had. And then we'll have mu naught over 4 pi times eta 2 pi r dr omega over r. And then you can start to cancel a lot of things, because we have 2 pi over 4 pi, and it just cancels to over 2, and we have an r and another r, so those cancel each other. So it's really nice, actually, because it just ends up being mu naught over 2 times eta omega dr, which is a pretty simple thing to integrate. And now we are ready to integrate. So we're integrating between 0 and r because we want to find an expression for the total charge of this circle. So if we're integrating in a circle, then you're going from 0 to the outside r. Your lower limit is this center point, your upper limit is this outer part of the circle, and as you're integrating, you're finding the whole area of this whole, or the expression for the magnetic field of this whole area. So you integrate from 0 to r of mu naught over 2 times eta omega dr, and then, because you can just imagine a 1 here because there's no r value, once you integrate, these are all constants, so you can just pull them out, but you basically, this dr goes away because it's telling you what you're integrating with respect to, and because you can just imagine a 1, you can turn that 1 into an r. So you get mu naught over 2 times eta omega r. And then you're almost done, but you want this to be in terms of q instead of, not q. So we can resubstitute mu naught over 2 q divided by a for eta, because we just know that eta is the charge density, and that's how much charge is over that little unit area. Or now it's the area of the whole thing, but still, eta is equal to q divided by a. So we can resubstitute that, omega r, and then we know that area is just the circle, so we know that 2a is equal to just 2 pi r squared, and then this, I should have just crossed out this squared because the r itself doesn't cancel, just one of these r's. But r and r cancel, and then eventually you get just mu naught over 2 mu naught q times, this is an omega, it kind of looks like a w, but it's mu naught q omega over 2 pi r. And that's the expression that you can use to find the magnetic field at the center of the disk. Okay.